Welcome to The Explainer. Today, we are going to pull back the curtain on a super important idea that honestly keeps our whole high tech world from falling apart. It's called proportional control. And the crazy part, you're already an expert at it, even if you don't know it yet. Okay, so picture this. You're an engineer on one of those massive cargo ships, right? I mean, these things are literally the size of a city block. And all around you are systems temperature, pressure, water levels that need constant, perfect adjustments. Could a single person or even a team of people run around turning dials 24/7 to keep it all balanced? No way. It's completely impossible. So, what's the secret? How do these giants basically run themselves? So, here's how we're going to break it all down. First, we'll stick with that automated ship. Then, I'll show you how you're already a pro at this. After that, we'll get into the actual proportional rule and its language. We'll also look at one tiny little flaw in the system. And finally, we'll see why this is the absolute foundation of all modern control. Okay, first up, the automated ship. Let's dive in and see how machines really do take the helm. You know, the truth is, on ships like these, having a person manually controlling every little thing, that's ancient history. I mean, think about it. The sheer number of things that need to be adjusted constantly, second by second, it's just too much for human to handle. So instead, machines do the work. Automatic systems are in charge of pretty much everything. So you're talking about things like the boiler water level, the cooling systems for the engine, fuel flow, steam pressure. I mean, the list goes on and on. And all these critical, totally different systems are all run by the exact same simple and really elegant idea. And that idea is proportional control. All right, let's move on. Because this whole thing isn't just some high-tech concept for giant ships. Not at all. In fact, like I said before, you are already a controller. You've mastered this without ever taking a class on it. Just think about driving a car, something most of us do every day. If you look down and you're just a little bit under the speed limit, what do? You press the gas pedal. Just a little, right? But what if you're way below the speed limit? Well, then you push that pedal down much harder. See what you just did? Your action, how hard you press the gas, is directly proportional to how far off you are from your target speed. That's literally it. That's the secret sauce right there. Okay, so you've got the gut feeling for it now, right? The car example makes total sense. So let's get into the nitty-gritty and learn the official words engineers use to talk about what your brain and your foot just did automatically. First term you need to know is set point. It's super simple. The set point is just your goal. It's the target value you're aiming for. So in the car, your set point was the speed limit. On that ship, for a boiler, the set point might be a water level of exactly 50%. It's what perfect looks like. Okay, next up is the measured value. Now, if the set point is your goal, the measured value is your reality. It's what the speedometer is actually reading right now. It's the real-time data from a sensor saying what that water level actually is. This is the feedback. It's the system telling you, here's where we are at this very second. Right, so what happens when you compare the goal with reality? Well, the difference between the set point and the measured value. That's what we call the error. Now, don't think of error as a bad thing like you made a mistake. It's just the gap. It's the distance the controller needs to close. A big gap is a big error. A small gap is a small error. Simple as that. And that brings us right back to the core logic of the whole thing. It's a two-step dance. Step 1, calculate the error. How far are we from our goal? Step 2, apply a fix that is proportional to that error. A tiny error, you get a tiny little nudge. A huge error, you get a big, forceful correction. That's proportional control. So you might be wondering, how do you tune this thing? How do you make the response just right? Well, engineers use a setting called the proportional band, or PB for short. You can think of it like a sensitivity knob. If you have a really small or narrow proportional band, the controller gets super aggressive. It reacts fast to even tiny errors. But that can make it unstable, kind of jittery. On the other hand, if you use a larger or wider band, the response is much smoother, more gentle. It's a bit slower, but way more stable. And the whole game is just finding that sweet spot right in the middle. Okay, so this system sounds amazing, right? It's simple, it's fast, it's pretty stable once you tune it. It's almost perfect. But there is one tiny little built-in flaw that we have to talk about. And that flaw has a name. It's called offset, or sometimes steady-state error. And here's the catch with proportional control. Remember how the correction gets smaller as the error gets smaller? Well, what happens when the error is really small? The correction becomes so tiny, so weak, that it's just not strong enough to overcome the natural friction or resistance in the system. So the system just settles. It gets really, really close to the target, but it can never quite get there. Yeah, check this out. Let's say your set point for a heater is exactly 80 degrees Celsius, but the system stabilizes and just holds steady at 78 degrees. That little 2-degree gap, that's the offset. The controller is still applying a tiny bit of power to correct it, but it's just not enough to push it over that last little hurdle. So, how do engineers solve this problem? I mean, sometimes close enough isn't good enough. Well, this is where they add another layer of smarts called integral control. When you add that in, you get the famous PID controller. And that I in PID, its entire job is to hunt down and completely wipe out that nagging offset over time. But that's a whole other story for another day. All right, so let's put it all together. Even with that tiny flaw, let's talk about the big takeaway here, why this idea is so foundational. So let's boil it all down. Proportional control is the absolute workhorse of automation. The output is always proportional to the error, and that error is just the gap between your set point and your measured value. It's simple, it's fast, and when you tune it right, it's really stable. It is the first most fundamental building block in pretty much every automated system out there. And that's why they say this. If you can really truly get your head around proportional control, you've taken the biggest step there is to understanding how all these incredible automated systems work, whether it's a giant ship or the thermostat in your house. So now that you know the secret, you're going to start seeing it everywhere. When your cruise control kicks in on a hill, or you hear your air conditioner turn on, that's it. You're seeing that simple, proportional logic doing its thing. So my question to you is, what other invisible systems are all around you, quietly running the world using this one simple rule?